We are going to talk about probability and introduce the idea of probability today. An experiment is an activity with observable results. So, an experiment doesn't have to be what you typically think of as a chemistry experiment, let's say. A lot of times, all we're doing is observing what happens in a certain scenario. A sample point is an outcome or a result of that experiment, an element. If we go back to our ideas from our set theory. Sample space is the set of all possible sample points of an experiment, so this is like the universe. And then we have what's called an event. An event is a subset of your sample space for an experiment. So a lot of the same ideas as set theory, we had in sets the universe, we had subsets of that universe, and we had elements inside there. So once we move over to probability, we're sort of talking about the same things, they just get new names. So we'll be talking about the sample spaces, events within that sample space, and sample points inside there. Okay, so here's our first experiment. Our first experiment consists of spinning the hand of this colored disc and observing the region in which the pointer stops. And we're saying if it lands on a line, we will just spin again. What is an appropriate sample space for this experiment? Or again, that's the idea of what's the universe that we are then talking about in this case. Sample spaces are usually denoted by the capital letter S, and sample spaces are sets. So we want to write the set of all of the outcomes that you could get if you spin this spinner. So I'm going to just use letters to represent them. I'm going to say R for red, W for white, P for purple, G for green, B for blue, and O for orange. Sorry. Okay, so that would be our sample space. Those are all of the outcomes that we could possibly get. Give the event the spinner points to the color purple. Okay, so remember, an event is just a subset of that sample space that we already gave. So I'm going to call this event E. Capital E is a lot of times used for events. That's got to be a subset of S, and if we're specifically talking about pointing at purple, that would be the event with only the sample point P. And that is a subset of S. What about the event, the spinner points to a primary color? I'm going to call that event F. E and F are typical names, letters used for events. So if it's going to point to a primary color, the only two colors that I see there that are primary colors are red and blue. Yellow is another primary color, but it's not on our spinner. So that would be my event for spinning a primary color. Okay, what if we have the sample space of the set 1, 2, 3 associated with some experiment? List all events of this experiment. How many events are there? So again, we just have to, we've done this question before, we just have to make a vocab change. Events are subsets. So we want to list all of the subsets of the set containing the elements 1, 2, 3. So when we list subsets, remember that the empty set is always a subset of every set. We would have the set just containing 1, the set just containing 2, the set just containing 3. Then we would have 1 and 2 together, 1 and 3 together, 2 and 3 together, and finally we could have the entire set is a subset of itself. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 events in this case, and remember, again, we can always do 2 to the n power. That's our formula for subsets. So 2 to the third in this case, there were 3 original elements, gives us 8. So some of these questions are going to be like repeat, but it just with that definition word change to make them apply specifically to probability to experiments now. Suppose there is a set of 5 students working on a project and they must choose 2 of themselves to be the presenters. How many possible ways can the students decide this? That is, how many events are there? Okay, so there are 5 students and they need to choose 2 of themselves. And in this case, there is no ordering. Neither of these students has a specific title, so the order doesn't matter here. I'm going to write that down. Order doesn't matter in this choice. So you may find yourself doing combinations or permutations again in this unit. So if we want to choose out of the 5, 2 students, we want to do a 5, choose 2. So it looks like there's 10 ways or events in this sample space. Okay, let's see. A person chooses a random letter from the word coffee. Give the set that represents the event E, the letter is a vowel. Okay, so this is going to be a subset. And again, event is just a subset. So the elements or sample points that I write in here have to be vowels. So there's an O and there's an E. And again, we don't write them more than once. So that would be my entire subset or my entire event. Let's write a few more sample spaces just for practice. So sample spaces, again, are just sets of every possible outcome of a certain experiment. So what if we do an experiment where we flip a coin to obtain either a heads or a tails? Okay, so my sample space in this case would be H and T. I flip these coins, I either observe a head or I observe a tails. Those are the only observations that I could make. What about we flip a coin twice to obtain heads or tails followed by another heads or tails? Okay, so in this sample space, we have to flip the coin twice before we make our final observation. So if I flip a coin twice, I could observe heads heads, or heads tails, or tails heads, or tails tails. And that would be all of the different observations that could be made if we flip a coin twice. What if you flip a coin twice to see whether the outcomes match or differ? Okay, so in this case, I have to flip the coin twice before I can make my observation, and my observations are simply that either those coins matched, so M, or they differed, D. So in that case, I really didn't care if they were heads or tails. That becomes irrelevant in my sample space. All I cared about was whether they were the same or different. So those become my sample points. You flip a coin twice and you count the number of heads. So notice that all of these are flipping a coin or flipping a coin twice, but the sample spaces change based on what it is specifically that we're trying to observe. So in this case, I want to flip the coin twice, and then I'm going to make my observation of how many heads did I see? Well, I could have seen 0 heads, or I could have seen 1 head, or I could have seen 2 heads. Okay, for the last one, it says flip a coin to obtain heads or tails, and then roll a die to obtain the number 1 through 6. I'm going to write this a little bit smaller. This is going to be a much larger sample space because I could observe a heads 1, a heads 2, a heads 3, heads 4, heads 5, or heads 6. And then I could also observe tails 1, tails 2, tails 3, tails 4, tails 5, or tails 6. And we know from our prior work that if we wanted to know how many there would be, we could use that multiplication rule since there's 2 possible outcomes for the first heads or tails, and then there's 6 possible outcomes for the second, that we should get 12 total outcomes, and I have indeed written 12 different outcomes out there. So it says, notice that if your experiment gets complicated enough, a tree diagram can be helpful to find all the elements in the sample space. So we may know by this how many there are, but if you have ever trouble kind of imagining, visualizing what they all are to list them, then making a tree diagram can help you to visualize those.